Hi, hello friends, welcome back to Max Lecture Series. In this series, we will be learning how to solve various functions under integration in vector calculus by using various theorems. Of course, so far we have been discussed about Green's theorem, Stokes theorem, anything else? No, only we have been discussed about two theorems. In this session, we are going to learn something new. Let us see. If you observe the given function, if R vector is the position vector of any point on a closed surface, yes, that encloses the volume V, then double integral of R vector dot ds vector is equal to dash. When the moment we are observing simply this type of question, of course some of you might not having any idea. Let me tell you first, whenever they are talking about this name, what is this name? Position vector. Whenever they are telling that the given vector is position vector, it means on a space we are considering some generalized position from the origin. It means what, sir? Nothing is there. Position vector means from 0, 0, 0, three-dimensional vector first. From 0, 0, 0, we will be considering any one random point on a space. Any one random point x, y, z. Now, position, the distance between the origin and any one random position on a space will be simply considered as positional vector. This can be written as, this is, see, let me consider this point is x1, this point is x2, this point, sorry, not x2, x1, y1, z1. Or we can simply write the answer. Why are you going up with this much complexity? Nothing is there. See there, this is the point that we have finalized. Now find out the distance from x minus 0, first distance x minus 0, that is x2 minus x1. We can say like this, such that this can be written as x into I vector, three-dimensional vector, right? Similarly, y2 minus y1. So that is y minus 0, simply y into j vector, plus z2 minus z1. Simply that will be z times of k vector. So whenever they are talking about the position vector, now you should remember that they are talking about this one only. That's all. Do remember always. Okay, come back to the question. First we got some idea what is position vector. Now position vector of any point on a closed surface, yes, that encloses the volume. See here, if you observe, given it is surface integral, that is double integration. Line integration means single integral, surface integral means area, that is double integral. Volume means triple integral. They are talking about triple integral. Now, which theorem is interconnecting surface integral into volume integral? That is the question now. Sir, have you heard about this anywhere? Yes, there is a theorem which will be helping us. Like we know, with the help of Green's theorem and Stokes theorem, we are converting line integral into surface integral. We saw both Stokes theorem and Green's theorem are dealing with the line into surface. Who is there to help us to convert the theorem to surface to volume? This type of conversion will be easily bringing the answer within 1 or 2 steps. That's why we are doing here basically. Let us see. Let me write. Yes, one more theorem is there which will be helping us to convert the double integration into triple integration. What is that? Suppose if you are having a vector field and you are doing the integration with respect to surface integral, you can transform it into volume integral. Volume means that is simply called triple integration. So volume integral, but when the moment you are converting volume integral, f will be converted into divergence of f, very important, and then you can put volume integral dv. So v stands for volume, here s stands for surface, v stands for volume, and f is our vector field. This operator del, we know, see, I told f is a vector field. I am repeating, f is a vector field. Whenever you are keeping operator del with a vector field, then operator del will be named as divergence of f vector. So this can also be rewritten as divergence of f. I told you, if you are with the nearby operator del, if you are having a scalar function, then del can be written as gradient. If you are having a vector function, then the same del can be written as what? Divergence. That's all. Anyway, we brought the relation between surface integral to volume integral. Of course, this theorem is simply called what? Divergence. That is Gauss divergence theorem. So this is simply called Gauss. 1 minute. Yeah, this is simply called Gauss divergence theorem. Just make a hint. This is simply called Gauss divergence theorem. It's most beautiful theorem, we can bring the answer easily with the help of this. Okay, sir, let us see. In place of first, let me go ahead with the surface integral. According to the given data, in a surface integral, they are considering a position vector R vector into ds vector. Let us convert it into triple integration first. I am converting into triple integral form. Then here, the position vector is going to be, what will happen? Position vector, that is divergence of f. We have it can be rewritten as divergence of R vector into dv. I hope you all understood how to do this. Fine, sir. So from here, what we are going to do is, for the position vector, if you are identifying the divergence of R vector, see, we know R vector stands for, it can be written as x times of I vector plus y times of j vector plus z times of k vector. That's all. Now here, this is going to be, it can be further written as divergence of R vector, means we have to differentiate. We know how will you write down the divergence of R? This can be written as dou by dou x into I vector plus dou by dou y into j vector plus dou by dou z into k vector. That is divergence stands for. Then R vector can be written as x into I vector plus y into j vector plus z into k vector. Simply stands. So from here what we can say, dot product of I dot I will become 1, differentiation of x with respect to, see, dou by dou x, differentiation of x with respect to x will become 1. Second, again j dot j will become 1, differentiation of y with respect to y will also become 1. Similarly for z it will also will become 1. So finally it will become a constant value 3. Okay, sir, that is very simple. After that, it is very important. See, it's a simple constant. It will become a simple constant. Now, what you can see is, limit is not given for triple integral. So, this is indefinite integral. I can simply write triple integral can also be written as like this, representation. See, if I am putting V, it stands for volume integral. It means representation of triple integral in terms of single integral. We can write like this and we can put V, that is volume. And we got divergence of R can be written as simply 3 times of dv. This is indefinite integral. Without limit, we are going to simply integrate it. That's all. Now tell me, what is 3 is a constant. If we integrate dv simply, what will happen? It will give you 1. So dv will become v. That's all. So the correct answer is 3 times of v. I am repeating. Double integration, surface integral can also be simply written like this. If I will put S, it stands for surface. It doesn't mean that we are doing single integration here. S means double integration can be represented like this. So triple integration, since the limit has not been given here, I am just considering it is indefinite integral. We know definite integral means limit will be given. Indefinite integral means limit will not be specified. You can directly simply integrate the function and write your answer. V stands for volume here, we know. So the correct answer is 3 times of V. That's all. I hope you all got the answer, and I hope you all understood how to apply divergence theorem here. So now we know how to apply Green's theorem. We also know how to apply Stokes theorem. We also know how to apply divergence theorem. And the Green's theorem, Stokes theorem, both are giving the interconnections between line and surface integral, whereas our Gauss divergence theorem will be helping us to bring the relation between surface integral to volume integral. This is all for this lecture. In the next lecture, I will be coming up with one more question. Thank you all.